Hi, this is a little very informal and probably somewhat rough lecture about representing repeated fractions as polygons. Um, so I wanted to just throw some images at you first. Here's an image. Here's another one. And what all of these images have in common is they're all derived with the same sort of essential function with slightly different variables punched in, and I think we can agree that they're quite baffling and quite pretty. This one kind of has a sort of spiral to it, if you can see that, and it even has a little tooltip you can see in tiny letters there. 167 semicolon 29. I'm going to talk about what that means, but um, I can make many of these images, and none of them will be exactly the same unless I, of course, punch in this same set of parameters. What these are they're polygons, and they represent repeated fractions, as the title implies. And so we're going to do a little bit of math, but mostly the purpose of this is to look at pretty pictures and maybe try to speculate on the arithmetic basis of how those pictures come about. So it would involve a lot of what's called modular arithmetic. I don't know modular arithmetic, but so we're going to basically avoid talking about modular arithmetic in a whole lot of depth. And in fact, I'm going to be posing a series of questions that can be answered with maybe some strategically placed modular arithmetic. But as it is, the questions are going to remain unanswered, and the purpose of this lecture is to just look at pretty pictures and talk a little bit about some patterns that I see that are just worth admiring and worth thinking about from a mathematical perspective. Okay, every fraction whose denominator is prime and whose denominator is not a factor of the base that we're working in is a repeating decimal in that base. So sometimes such decimals gather into a single cycle, i.e. they use the same repeating digit pattern but in a rotated order. So this first example that I'm giving is looking at n over 7. The denominator is 7. The base is 10, which is the base that we normally work in because we have 10 fingers. But I think some of you might be perfectly familiar with these repeating fractions. This is 1/7, 2/7, 3/7, 4/7, 5/7, and 6/7. Of course, 7/7 is 1, has no repeating fraction, of course. But you'll also notice, and I think a lot of people noticed this when they first started doing decimals, the digits in here, 142,857, are the same as the digits in here, 142,857, 142,857. They're just in a different order. So this one starts with 1, this one starts with 2, etc. And you can imagine they're going to get these numbers are going to get larger, but I'm not really interested in those numbers getting larger. I'm interested in the order in which those digits appear. Okay, so this one starts with 1, 4, and then the one starting with 4 is here. The one starting with 2 is here. The one starting with 8 is here. 8, 5, 5, 7, 7, 1, and then back to 1. Okay, so I'm not interested in their rising order, but their numeric, or what I want to call their cyclical order. Okay, so sorted in the order of this cycle, they're going to look like this: 1/7, 3/7, 2/7, 6/7, 4/7, and 5/7. And you can see the digits of the repeating cycle as they kind of shift to the left with each line. Okay, so n over 7 in base 10 is represented by this sequence of numbers: 1, 3, 2, 6, 4, 5. This now a little bit of math. This is the same as looking at decimal expansions of 1, 10, 100, 1,000, 10,000, 100,000, and a million modulo 7. Okay? So what is this little formula doing? It says 10 to the x um, mod 7 in the range 10 to the 0, 10 to the 1, 10 to the 2. That's just these numbers. And if I look at each one of these numbers modulo 7, then it spits out this series of numbers. And that number, as I say, is the same as the number series up here. Okay, and now we get to the pictures. If I map these numbers 1 through 6, if I map the numerators 1 through 6 onto circle points, then you end up with this mirror symmetrical polygon. Okay? Down here at the bottom left is always going to be the point 1, and it goes straight up to 3, or let's count them, 1, 2, 3, 4, 5, 6 going around. It's basically a hexagon, right? But point 1 connects to point 3, point 3 connects to point 2, 2 to 6, 6 up to 4, 4 to 5, and 5 back to 1, corresponding to this sequence. Okay? And so that is the picture, or the polygon, for denominator 7 and base 10. I'm just going to write 10 here. Okay, and it evaluates to that. Right, and so what this is going to require you to stretch your mind a little bit is you look at this and you just see 4 triangles. It's not a regular polygon. Okay, this is what you're used to seeing as a regular polygon. But I want you to think of this. This is, of course, an irregular polygon now, and that's even more irregular. But I want you to be able to tolerate the idea of these edges. This still has 6 edges, but tolerate the idea of these edges crossing each other and crossing each other. So there, I've still got a hexagon, but it looks like 4 triangles. Still a hexagon. And that's something we just have to learn how to tolerate. This can cross over here, and then we've got 1, 2, 3, 4 triangles and 2 quadrilaterals. Still a hexagon. Okay, but that's how these none of these polygons are going to be regular polygons, with some exceptions. But I just want to do a side note here about polygons in general. Here's the pick 7, 10, right? 7 denominator 7, base 10. You might also be more accustomed to seeing this kind of thing looking like that. It's very hard to see, but that's just the edges of the polygon and all of the shapes. It's hollow, very hard to read. And this is not how I'm going to be representing these. This makes it, here it's a little easier to see. I've made the lines a little thicker. This is not how I'm going to generally represent things, because as these polygons get more complex, it's going to be very hard to see what's going on. So this one has 6 vertices. This one has 910 vertices. You can sort of see what's going on, but if you zoom in here, you've got this black zone where you can't really see anything anymore, and it's much easier to see it if I do what I've been doing before, which is having these sort of the shapes that are formed being black and white. So this is basically the equivalent of this one, whereas this one is the equivalent of this. Okay, easier to understand as a polygon in simpler shapes, but when it gets more complex, it's very hard to see any details like it is. This is wonderfully detailed, at least in the resolution of my screen. If you're watching this on YouTube, of course, it might look horrible. No worries. You'll get plenty of appreciation for how these things actually look. Okay, so let's take this away. All right. So that was denominator 7, base 10. Decimal expansions for some denominators gather into more than one cycle. For example, in the case of denominator 13, there are 2 cycles. Okay, and this is basically the same. Let me just show you that in the way that you're used to seeing. 1/13 is 0.07932. 0.76932. I'm talking too fast. 0.76923, 0.76923, 0.76923 repeating. 10/13 is 76923 repeating. 9/13 is 6923007 repeating. 12 is 9230766 repeating. 3 is 230769 repeating, and 4 is 307692 repeating. Okay, so you can again see the digits kind of drifting to the left from line to line. But in creating that cycle, I don't actually touch half of the numerators. Okay, so cycling around from 1/13, I'm never going to hit 2/13, because 2/13 is in its own universe, its own little cycle. 153846, 538461 makes 7/13, 384615 makes 5/13, and so on. So 2 cycles, each one of the same length, namely 6 digits, and so we're going to get 2 images, and those 2 images are also hexagons. And as it happens, those 2 images are also mirror symmetrical with each other. So just to remind you how to read this, this is 1, 10, 9, 12, 3, 4, back to 1. And this one is 2, 7, wait, no. Yeah, 2, 7 is at the top here. 2, 7, 5, 11, 6, 8, 2. 2, 7, 5, 11, 6, 8, 2, 1, 10, 9, 12, 3, 4, 1. Okay, so those are those 2 images. The actual number of cycles, we've seen 1 cycle and we've seen 2 cycles. The actual number of cycles for every prime denominator is, like many prime number related phenomena, quite unpredictable. So staying in base 10, here are the numbers of cycles for the first 50 prime numbers in base 10. And you'll note that for 2, I don't have 2 and 5 are by themselves, but the first argument in each of these pairs is the prime number, the numerator, and the second number is always going to tell you how many cycles are formed. And everybody knows about 1/3. 1/3 is going to be 0.3333, and 2/3 is going to be 0.6666. Those 2 don't have the same digits in them. In fact, each one only has 1 digit. That's quite a special case. But in 1/11, you do have 5 cycles, and maybe if you have dealt with repeating fractions a lot, you'll know already that 1/11 is 09090909, 2/11 is 18181818, and so on. Then 272727, 363636, 454545, 545454. Those 2 are the same, are in the same cycle, and so on. 13 we've already seen, has 2 cycles. 17 has 1, and so on. And you'll see that some of these numbers get quite big. Where's an example? So 141th or 141st, I guess you'd say, forms 8 different polygons, and each one of those polygons is well, how many sides are in each polygon? Well, remember that when we had 7 and one cycle, it was a hexagon, and that number is always going to be based on the denominator minus 1, right? 7 minus 1 is 6. I get hexagons. 41 minus 1 is 40, and I'm going to get 8 different hexagons, so each one of them is going to be a pentagon, because 8 times 5 is 40. And what we had before, 13, with the denominator 13, 2 cycles of 6 points each, so 2 hexagons. 2 times 6 is 12, which is 13 minus 1. You'll get used to that in a little bit, but you know, with 73 I have 9. What's the largest number up here? Um, maybe 9 is the biggest number of cycles. Anyway, we'll get to it. All right, so according to the above list, you should get 4 different figures for denominator 53, and indeed, here are those 4 figures, and each one of them has what we're doing is we're distributing 53 minus 1, 52 points. We're distributing 52 points around the circle onto 4 different polygons. They're pretty funky looking polygons. But each one of them has 13 points in it. 13 times 4 is 52. And so n over 53 makes 4 different polygons, and that's what it says up here. N over 53 makes 4 polygons. And for n over 211, I'm going to get 7 polygons. And I've made them a little smaller so they fit on one line. And notice that these polygons up here are asymmetrical within themselves, but they form these kind of twin pairs. This one is a mirror image of this one. These 2 little wine glasses, I guess, or brandy glasses on there that are kind of on edge. Those are mirror images of each other, and these other 2, I don't know how you describe them, are mirror images of each other. But for these 7, these are all symmetrical in and of themselves. Okay, and in fact, so these, how many edges or how many vertices or how many vertices or edges are there in each polygon? Well, 210 we go down to 211 we go down to 210, and with 7 of them, 210 divided by 7 is 30. Each one of these is actually a 30gon, has 30 edges or 30 vertices. Okay, so what are those? That's a tridecagon? No, that's, I'm not sure if tridecagon is our, I'm not sure. Vicentagon? I don't know. What is a trentagon? Maybe these are called trentagons. They're 30-sided. Okay, so this chart is just telling us how many are going to be in each cycle, and there you see 211 with a denominator of 211. I get 7 different polygons, each with 30 edges, which I'd have to figure out that there are 30 edges. I'm doing a little bit of math. Okay. If there is an even number of circle points in an image, such as here, a 30gon, then that image will be mirror symmetrical. However, if there is an odd number of circle points, then the images can be mirror symmetrical in themselves, or they can be grouped in pairs of twins, each one being a mirror image of the other. And that's what we had up here. Yeah, these are pairs of twins, pairs of what in chemistry is called enantiomorphs. They are the same backwards and forwards. That term enantiomorph came up in Breaking Bad, if you watched Breaking Bad. Yeah, they're mirror images of each other. In chemistry, you sometimes get that a chemical will simply be its own inverse somehow, and the enantiomorph is poisonous, and the other one is not. Okay, so that's what those are. Those are mirror symmetrical pairs rather than images that are mirror symmetrical within themselves. And so here are 2 more, a little more complicated examples. Each one is a pair of twins, but 293 forms 2 different shapes that are mirror symmetrical in and of themselves. 283, they form a pair of twins. Okay? I guess 290. This one has 146 edges. This one has 136 edges. So they do have an even number of edges, but this one's asymmetrical and this one's symmetrical. A pair of symmetrical figures. Okay. I hope you can see that these 2 are mirror images of each other. That's always going to be the case. That if I have an even number of asymmetrical ones, they're gonna pair off. Okay. the more polygons there are, the fewer the edges per poly. All right, this is clear. The more polygons there are, the fewer edges there will be per polygon. So with a denominator of 109, I'm going to get one 109agon. But with a polygon of with a numerator of 127, I'm going to get three 42agons. 42 times 3 being 126. So the extreme cases seem to be, yeah, 101. Oh yeah, this one I overlooked. 101, denominator 101, has 25, forms 25 different polygons, and they look like, whoops. And you can see why that is. These are the repeating fractions. 0099 is 4 different digits, yeah? But after 101th is 0099, and so on. But if you look carefully, you're going to find 0990 is a cycle of that, and then 9900 is the next one, and then 9009 is here. Yeah. So those 4 numerators form a cycle. 0198 is going to be followed by 1980, followed by 9801, followed by 8109, if I can find it. Oh, 8019, excuse me. There it is. Okay. So actually I'm getting 4-point images with 4 points in them. Denominator 100 and 101. We have 100 fractions, or 100 repeating decimals, and we're going to get 25 polygons, and each polygon is actually a quadrilateral. They have 4. They're going to have 4 edges, and let's see what those look like. Yeah. So this is the geometric equivalent of. Whoops, sorry, I shouldn't have done that. This is going to be the geometric equivalent of these repeating fractions mapped onto circle points, and they look like this. Okay, yeah, they look like a bunch of bow ties or butterflies or what have you, but these are quadrilaterals. These are 4-edged images, right? And you can see how one of them is kind of narrow here, one of them is kind of flat and tall, and then at the end is another flat and tall one. They all have different sizes, but what they all are, it's a little bit harder to see the fact that they are actually inscribed into unseen circles. Yeah. So here the circle the circle at this one has to go through all 4 of these points. This is a bit hard to see, but that circle is kind of going to be all the way up like this, if you follow my cursor. Whereas this one, the circle is going to look like that, kind of. It's going to be crossing through those 4 points, and this one, it's a little bit easier to see how these are maybe all on the same circle. Okay, so they are all of different sizes, and that's just a matter of me not actually drawing the circle that they're inscribed in. But yeah, these are quadrilaterals, and we had 11 before, right? 11 breaks up into 5 different cycles. Remember, I was saying 090909 and 909090. Those are actually just 2 points, right? So you can't have a 2-pointed polygon. If you try to draw them as polygons, the computer is going to try, but you're going to end up with these empty spaces, and these spaces actually, you'll have to take my word for it, are not empty. They're actually these are line segments in here, and they're not being rendered because line segments are not polygons. Okay, and in 30 with n over 37, I think these are going to end up being triangles. There, if you look at the original list, under 37, yeah, with 37, I have 12 polygons, and each of those has 3 points in it, and that's going to look like this. Each one of those is a triangle. You can count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 polygons. And just look at the repeating fractions for a second, you'll see they have 3 digits before they repeat. So 027, 270, 702, and this is the last time, well, not quite. This is one of the last times we're going to be looking at repeated fractions. And we're going to start looking a lot more at images. Okay. So far, we've been working in base 10, which is the the number system that we use in daily life. But the same conditions will hold true for all other bases. So here is 1/7. We're going back to the denominator 7. We're going to n over 7 in base 5. Okay. Remember that base 5 only uses the digits 0, 1, 2, 3, and 4. And here is 1/7 in base 5. 032412. This is 2/7 in base 5. 120324. 3/7 is 203241. 4/7 is 241203. 5/7 is 324120. And 6/7 is 412032. And it's the same pattern. I mean, the 2 is appearing twice, right? But the pattern is just cyclical. I'm going to try and show you that in order. Whoops, that's not quite it. Yeah, it's not here in order. You're just going to have to imagine it. 1 is followed, yeah, there's 032412, 324120, 241203, 412032, 120324, 203241. That would be the represented in cycles, and that gives us this list. This is the same list from which we're going to end up deriving our polygon, and the polygon is the same as the polygon in base 10. Right? But here we're reading the same polygon. Before we were reading it as 1, 3, 2, 6, 4, 5. This is going to be 1, 5, 4, 6, 2, 3, back to 1. We're reading the same polygon backwards. We're not going to notice which direction it's being read in. Of course, the image is the same. And indeed, you know, this is 1, 3, 2, 4, and then 5 comes next in the series, and then 241203 comes next in the series, number 4, and then 6, and then 2. Okay, you get the picture. Okay, these are the same. We end up with the same polygon. In base 5, looking at denominator of 13, I actually end up with something very different. These are actually going to break up into 4 different, 3 different cycles, excuse me, right? In base 10, denominator 13 had 2 cycles. In base 5, denominator 13 is going to have 4 cycles, or 3 cycles, excuse me. 1, 5, 12, 8, and here again you see the digits shifting to the left. 2, 10, 11, 3, and 4, 7, 9, 6. And you can see all of them represented 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, 13. So they're all accounted for here. Okay. If you look at those as images, they look like this. And of course, these are the familiar bow ties that every quadrilateral is going to form in this universe. Yeah, these quadrilaterals have are reminiscent of the ones we had upstairs with the denominator 101. Yeah, here they are. Let's just look at those again. Yeah, same kind of thing. So these are quadrilaterals. For comparison, here's what we had before. These are the same. N over 13 in base 10. We had these 2 hexagons. Okay, so just like we did with base 10, here's a list of the first 50 primes with their corresponding subcycles in base 5. I'm not. These numbers, of course, are not in base 5, but these are the. When I try to represent, denominator 11 in base 5, I'm going to get 2 cycles. Here's a nice big one. With denominator 181, I'm going to get 12 cycles of 180 divided by 12 edges each. With the denominator 191, I'm going to get 190. I'm going to get numerators 1 through 190. And there are going to be 10 images with 19 edges each, right? Okay. So here's another arbitrarily chosen pair of polygons to compare with each other. This is denominator 97 in base 5 and denominator 97 in base 10. And in each case, each one forms a single cycle. Okay? So that's kind of nice. This is 97 in base 5. This is 97 as a polygon, denominator 97 in base 10. Okay. Cool. And just to give you one more arbitrary example, the number of subcycles per denominator in base 12. Okay. And the reason I'm pointing out this one is you'll note that for the number 2 and the number 3, there are no polygons because 2, 1/2 in base 12 is not going to be a repeating fraction, and 1/3 in base 12 is also not going to be a repeating fraction because they are factors of the base. Okay, just like 5 doesn't create a repeating fraction in base 10, 5 does create a repeating fraction in base 12. Okay, so that's just a given, just an extra example. All right, so now let's look at our first question. This is a modular arithmetic question, and we're not going to answer it here. These are kind of left as exercises for people who are fans of modular arithmetic. I can say that I'm a fan, but I'm not an expert, and this is a question that I might be able to answer, but I want to leave as an exercise, partially because I'm too lazy and I'm not entirely sure that I can answer it reliably. How many cycles will be formed with a given denominator and a given base? Excuse me. Okay, how many cycles will be formed with a given denominator and base? 7 base 10, 1. 11 base 10, 5. 13 base 10, 2. But is there some formula that lets me predict that? Second question, when are the polygons going to be self-symmetrical, and when will they instead divide into mirrored pairs? We know a little bit about that because if there's an even number of edges in the polygon, it's going to be symmetrical. But if there is an odd number of edges in the polygon, when's it going to be symmetrical and when is it not? That's an open question. Okay. Interestingly, when the base is a perfect square, then there won't be any decimal expansions with an odd number of cycles. To put it a different way, there will be always an even number of polygons formed. You're never going to get a single polygon. Okay? So 1/3 in base 4 forms 2 polygons. 1/5 n over 5 in base 4 forms 2. But if you just always look at the second argument in each of these pairs, it's going to be an even number. Okay, this is true for all powers of 2, all perfect squares, I should say. 4, 9, 16. Here's 16. The calculation is pretty fast. It's always an even number of polygons at the end. An even number of polygons are formed. 36. And here's base 100, which of course is, 10 squared. These are all the perfect squares. And again, the number of polygons is even in each case. All right, so this is my second sort of modular arithmetic, modular algebra, or a modular arithmetic question. Why do perfect square bases only create an even number of polygons, regardless of what prime denominator is being used? Okay, so the rest is all pretty pictures. For sufficiently large primes and reasonably small bases, one can begin to recognize just from looking at the image what base is being used. the edges of these polygons seem to gather into nodes, with the number of nodes equal to one less than the base. Okay, so here is a relatively large prime as the denominator, 433, in base 10, and that image looks like this. Okay. Yeah, there's a tremendous amount of detail here, but I think you can see that here at the top, there's this sort of figure, kind of looks like a corn, like a bunch of corn stalks tied together. But you could see that that image, kind of as you rotate around the circle, it's kind of repeating itself all around. If you count the number of these, there's one here, 2, 3, 4, 5, 6, 7, 8, 9 of these little nodes. And if you zoom in on them, I'm going to do a little bit of that. I want to zoom in on these. They kind of, yeah, this is a node. This is actually from the same image. This is denominator 433. And as I go around the image in detail, they kind of look like volcanoes now and less like corn stalks. But I'm just going to call them nodes. Yeah, they gather into these little nodes, and if you zoom in even more, you can see a lot of lines seem to kind of converge on this point here. But what's really happening is I'm getting this optical illusion happening where this edge of this volcano, it kind of looks like a curve, but that curve is being made by straight lines, right? It's just being formed by straight lines, but the volcano itself is very easy to see. Very unmistakable kind of repeating pattern. There it is. And we'll look at one more. Okay. And the base is 10. The number of little nodes, volcano nodes, is 9. Yeah? Which is 10 minus 1, right? Base 10, 9 nodes. Base 10, 9 nodes. And here I've just to make it super clear, I've drawn the same thing with little arrows to indicate where the nodes are. And you can see that not only are there 9 nodes, but they're evenly distributed. They're very evenly distributed around the circle. Okay, these I'm sorry if you're colorblind, you don't really see them, but there are arrows that are pointed around the circle here. And I think even if you can't see the arrows, I think you can agree that these arrows demonstrate that the nodes are equidistant from each other around the circle. So that's cool. In base 6, you can clearly see, sorry, I'm going to hide that one for just a second. Here. In base 6, you can see 5 nodes. Those are the 5 nodes are evenly distributed. In base 23, kind of arbitrarily, I'm going to have 23 minus 1 or 22 nodes. It looks a little absurd, but and it takes a while to render, excuse me. Almost there. Come on. I've got my computer running, and I've got OBS running, the recording software. And now I apologize, this is really very hard to see, but if you squint, you can kind of see these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I started counting here, I'm sure. Even if they're hard to see, I did make a version of that with the red arrows again, and you'll be convinced, I think, that they are equidistant if you accept that the arrows are equidistant. These nodes, through some weird optical illusion, they sometimes look like they're slightly closer together in this image, but this proves that they're definitely all equidistant. Okay, and that's not hocus pocus. There is some mathematical reason for it. And notice that in base 2, there's only one such node, right? It's the same volcano thing, or this gathering thing here. I have another image of this that I can show you in slightly more detail. Yeah, this is base 3, but yeah, here it is in all its glory. A very big node. This is from a different image, but see how it kind of stretches out its behavior. It's got this very long, completely imaginary edge. This edge is actually being formed from several line segments, right? Straight line segments. It's a very nice optical illusion. And in base 2, yeah, this happens to be denominator 811 in base 2 forms three different polygons, and those three different polygons have 810 divided by 3 have 270 edges. Yeah, these are 270 agons, and each of them have that node in the middle. The other thing that I'm going to notice is that the virtual edge, this imagined edge, forms an almost perfect so-called cardioid. People who are familiar with polar coordinates and polar geometry are going to be familiar with the term cardioid. There are three little cardioids here, and they I think if you do the math, you're going to find that that is a perfect, quote unquote, perfect cardioid. Again, not a coincidence. Okay, so this gathering phenomenon, this node thing, the gathering into nodes can still be seen very clearly when there is more than one decimal cycle. So here is the denominator 1289. In base 2, I get 1, 2, 3, 4, 5, 6, 7, 8 images, but each of them has that cardioid shape, has that single node shape. And here is another example, again 1289 as the denominator, and now we're in base 3, and you can see it gathering into two, kind of collecting, each one of those images collects into two separate nodes, one on the left, one on the right. And this is the way they're orientated in the image we were just looking at, right? This is something in base 3. In fact, I can see it in the URL. The denominator is 607. The base is 3, and this 001 we don't need to be concerned with. But in base 3, I have two nodes, and this is a single image. So this is a 606-sided polygon, a 606-sided polygon with two edges. And again, because these are being rendered as so-called SVG or scalable vector graphics images, I can zoom in on them arbitrarily and get lots of super nice detail. Okay. Now we come to our fourth modular arithmetic question. How do we explain this morphology, these nodes, for low base polygon sets? Again, that's an exercise left to the reader. But moving on to other sorts of symmetrical dispositions, this is something mysterious. I really don't know how to explain it, but this with denominator 643 and base 137, I get this sort of clear white or whitish spot in the middle. If the polygon was rendered slightly differently, this would be a black spot, but it doesn't matter. It's the same principle. This little image is often recurring in these polygons as I explore them. I don't know what it is, but I can get it also symmetrically distributed. So here is denominator 607, base 476. I get two of these little images. And you can kind of see the ghost of a cardioid, a double cardioid image thing coming around here. It's okay if I'm the only one imagining that, but I think that's quite easy to see. But 476 doesn't bear any real relationship to kind of the way that 3 and 2, the number of nodes here is 1 minus the base. The number of nodes, the number of these kind of stained glass phenomena is 2 in this image, but 2 doesn't have any meaningful relationship to the number 476. So I don't know what these are, but there is a set of 2 of them. There is a set of 3 of them. And here's a set of 4 of them. Okay, and these were found sort of just by kind of exploring. I don't know why these things are being formed. It doesn't seem to have anything to do with the relationship between the denominator and the base of the formula. Okay, so much for these repeating figures. I want to talk now about the morphology of polygons with high bases. Okay, now before I was talking about base 2, base 3, base 4, forming nodes of base of 1 node, 2 nodes, 3 nodes respectively. Always base n forms n minus 1 nodes. Base 10 forms 9, etc. Now we're going to look at pardon this. This is these are variables. The hashtags are variables, but we're talking about, for example, we're creating images of, say, base 19. Of denominator 19 with base 17, or denominator 31 with base 29. Okay, I'm going to just expand this and then explain what's going on. These have just like we were talking about a repeating morphology here, these are also going to have a very noticeable morphological similarity. This is 7 base 5. You can see the tooltip, or maybe not, I'll read it out to you. This is 13 base 11. So always n, denominator n, base n minus 2. So denominator 23 base 21. Denominator 29 base 27, denominator 37 base 35, 47 base 45, and as they get more and more detailed and the denominators get larger, they start to kind of resemble a golf ball. And as they get even larger, it's really not a golf ball anymore, but this texture becomes more and more apparent. And on YouTube, this is going to start just looking like a gray nothing. But these are still polygons, right? The last one in this list, I don't know where I'm stopping. Yeah, the last one in this list has 599 edges, or no, 598 edges. This is the denominator 599 in base 597. So n and n minus 2 makes these golf balls. Okay. You can also see a repeating image with n and n minus 3. I didn't mean to well, evaluate it again, but there we go. It's not too slow. 11 base 8, 17 base 14. I'm choosing these. This isn't 7 base 4 because in 7 base 4 I'm going to get 2 images. I'm just selecting ones where the resulting image, there's a one image resulting. But as these get larger, again, these look quite different from each other. I've got this kind of star shape up here, this sort of 6-pointed star shape that gets smaller and gets even smaller and then gets even smaller and starts to vanish as this thing gets bigger. But as you look at the entire image, it starts to form something very distinct, namely something like a four-pointed star. And as it gets even more detailed, each of the points of those stars start to form their own little, it looks a little bit like the mythical star in the east from, the star over Bethlehem, if you will. Yeah, so those are getting more and more detailed and probably getting a little washed out on YouTube. The last one I have here, this is again, the denominator is 599, the base is 596. Before we had 599, 597. This is 599, 596. We get this 4-pointed star thing. So that was n comma n minus 3. This is n comma n minus 4. Again, I mistakenly re-evaluated it. It shouldn't take too long. Here is 7 base 3. We've seen that before. It's the same as 7 base 10. Don't overthink it, but 7 base 3 3 is 10 modulo 7, so they're going to be the same. I'm not going to go into that too much, but yeah, this is happens to be the same image as 7 base 5. And now as these get more intricate, at first they seem to be quite different from each other, but as they get more intricate, you start to see a kind of 5-pointed star structure in the middle. Yeah, these get more and more pronounced. See that? 5-pointed stars. And each of the points forms its own little star in the east kind of figure. Yeah, it looks very religious, actually. And this, I originally referred to these as modulo mandalas because of the kind of religious connotation that they seem to have. But here again, this is again the denominator is 599. As it happens, it always forms a single. It seems to always form a single cycle, at least among these high bases. But this is the most intricate one I'm going to show you. Has again a 5-part structure, and then the last group that actually does seem to have this. Again, I reevaluated it. The last group that seems to have this kind of intricacy is with n and n minus 5. We see an n and n minus 2, n and n minus 3, n and n minus 2 with the golf balls, n and n minus 3 was the four-pointed stars, n and n minus 4 was the 5-pointed stars. This is n and n minus 5, and you're going to get 6-pointed stars, but not yet. This is denominator 11 base 6, 17 base 12, again n and n minus 5, 19 and 14, 37 and 32, 53 and 48, and so on and so on. They're getting more and more intricate, and it takes a while for the kind of 6-pointedness of it to become apparent. Still not totally apparent, but now it's starting to form, and you'll see it on the readily on the most intricate one that we have here. Again, the denominator happens to be 599 in the most intricate one, and you can see these 1, 2, 3, 4, 5, 6 radiating points coming out of this star. Okay, and this can get more and more. As they get more and more intricate, what also happens is that these little beads, these little bulbs that are forming around here, those also get more and more pronounced. But we're not going to see those here. So I come to my next modular arithmetic question: how do we explain the morphology, the golf ball morphology, and the pointed stars morphology of these high base polygon sets? All right. So again, an exercise left to the reader, not just because they might be fun for you, but because they're a little beyond my ken. And I'm going to come on to the next point, which I'm calling embedded morphologies. We've seen those node shapes, and we've seen these kind of star shapes, node shapes associated with low bases, and star shapes associated with high bases. But these don't just occur on the top level. This is denominator 211. I've selected 5 images from the world of denominator 11. Denominator 211. The first one is in base 2, and you've gotten used to seeing that now. This has one single node in it, and it's a single image, right? And that image has this sort of cardioid, and the cardioid has these radiating, somewhat symmetrically radiating polygon edges virtually in it, but it looks kind of like a palm frond. And that morphology repeats in base 142, but this is not base 2 anymore. This is this embedded thing. It also shows up in base 22. It's kind of tiny, but you can see it. I might make these a little bigger. Kind of blow it up a little bit for you. Yeah. That cardioid shape is embedded inside here. This is in base 133, and here the cardioid shape has inverted itself, so now it's upside down, but it's still these kind of radiating palm fronds. And then this is base 116. don't worry about those numbers too much because I find them totally baffling. I don't know what they're doing there. But these two, actually, these look extremely similar, but they're not exactly the same. They're not the same image, right? But these are 1, 2, 3, 4, 5 different images from denominator 211, and each of them seems to have this little cardioid shape of different sizes: large, medium, and 3 of them quite small. But these images are not exactly identical. These two are very close to each other, but they're not the same. I promise you they're not the same. Okay. So that's embedded morphology, and I'm going to show you also with denominator 211. Here is the familiar bipartite 2-node shape in base 3, but and I want to call this a sort of a double cardioid shape. That is embedded inside base 72 here, and even smaller in base 111. You can see it here. I don't think I need to zoom in on these for you to see that, but I'm going to do it anyway. Okay, that's that one. This is this one. Okay, I can't explain these any more than I can explain. I mean, it'd be even harder to explain these as explaining the 2-node phenomenon that's happening here. But open question is of why those are forming. But I think the fact that they're forming is not a coincidence. There must be some sort of modular arithmetic reason for seeing them. Okay, and now I want to talk about how these large base morphologies. I refer to these as nested morphologies. Yeah, the morphology is inside. The familiar-looking morphology is inside some slightly more chaotic noise around them. But now I'm going to be showing you nested morphologies or embedded morphologies, where the embedded thing is familiar-looking, and the thing on the outside is familiar-looking. And here we've got these high base morphologies nested or embedded in low base morphologies. Okay, and the math I'm doing here, this if n was 19, this would be say 17, n and n minus 2. 1917 would be embedded in 19.4. So if n is 19 and k is 2, this is 1917 embedded inside 19.4. But don't worry about that too much. It's this digit k that's going to be constant. Let me just make this an m, because n is not the important thing. The important thing is this variable k. If k is 2, then this is n and n minus 2. This is m and just the number 4. What am I talking about? Let's take a look at this. Here, I want you to think of k as 3. Yeah, 293 is the denominator. 236. Sorry, 239 is the denominator. 236 is the base. So 239 minus 3 is 236, and that therefore k is 3. This is the familiar four-pointed star morphology, and that's going to show up in that similar image. Let me just show you these two images side by side. Okay, this is n comma n minus 3. This is n comma 5. Yeah, in base 5 we're going to have 4 nodes, and the thing that appears in the middle here is an n comma n minus 3 type of embedded four-pointed. This four-pointed star is embedded inside. Okay. This will become more clear as there are more examples, but this is n minus 3. this is n plus, this is 5, right? Here k is 3, k plus 2 is 5, n minus 3, 5. Here it is here is the familiar looking 5-pointed star that we get from the base n minus 4, right? N is 271, and this is n minus 4. I get the 5-pointed star thing. So the value of k is 4, and so the value of k plus 2 is 6. This is the n minus 4, and this is a different polygon in base 6, and you can see that this 5-pointed phenomenon is embedded inside of this image, right? But the base is 6, so therefore you're getting these 5 nodes. Okay, you got 5 nodes on the outside, a 5-pointed star on the inside, n minus 4 type image, and 6 base 6 on the outside. The nodes suggest base 6, and the image on the inside is this 5-pointed star thing. Okay, so here it was 3 and 5. Here it's 4 and 6, and here it's 5 and 7. Here's the 5. Here is an n minus 5 type image, and here is a base 7 image. I think you can see that this this pattern that you see in the middle of this one is coming up in very striking similarity in the image below it. And then let me do one with very high resolution. This is again an n minus 5 type of thing, but here it's much easier to see it as a 6-pointed star. Yeah, n minus 5 makes a 6-pointed star, and a base 7 image has 6 nodes, right? I've got the 6 nodes on the outside, but on the inside is forming this 6-pointed star thing that looks very similar to the 6-pointed star thing here. Okay. So this sort of embedded high base image inside a low base node system is what I'm fascinated by. Let's just look at these again without commentary. 3 and 5, 4 and 6, 5 and 7, 5 and 7 in a higher resolution. And at this very high resolution, you can kind of see what I was talking about earlier, that there are these kind of nodes forming. To me, this looks like a Venus of Willendorf type character, yeah? All right. So that's the 6th question. How do we explain these nested or embedded morphologies? And maybe that can be explained with modular arithmetic. Okay, and then the last question that I want to ask, and what I want to show off a little bit, this is a feature, a function that I created, which looks at all the polygons for a particular base, and it's called browsing. And if I just browse, say, a relatively small denominator, this is a collection of all of the polygons that are in groups of 6. This is all of the polygons that are in groups of 3. This is all the polygons in groups of 2. And this is all the polygons that are in groups of 1 in base 19. And it's nice to be able to just browse them. But what you'll notice is that they always come in pairs of sets. Yeah, the set of denominator 19 base 7 is the same as denominator 19 base 11. Okay. The denominator 19 base 8, these look the same as the denominator 19 base 12. The ones that are denominator 19 base 4 look like 19 base 5, and 19 base 6 looks like this one, right? 19 base 16. and then 19 base 9 looks like 19 base 17. And then finally, we get this these 6 pieces. 19 base 2 looks like 19 base 10. 19 base 3 looks like 19 base 13. And 19 base 14 looks like 19 base 15. But I'll bet you if you actually look at the original repeating decimals, one of them is going to be going, starting off, firing off clockwise, and the other one's going to start off counterclockwise. So that's kind of cool. But the question for me is, how do you get from 2 to 10, 14 to 15, 3 to 13? What is the relationship? Why does that relationship exist? Base 4, base 5, base 6, base 16. What do those pairs of numbers have to do with each other? I'm going to go to a higher base because I have more data, but these are far more complicated images. But you can see that with the denominator 211, these all are denominator 211. 211 base 2 shows up here again as base 106. Base 3 shows up again as base 141. And just to take a higher polygon set, okay, I'm probably going to get in trouble by not being able to find pairs of them. Oh no, here. This pair, 211 base 43. These 10 polygons in this group, you can see they're demarcated by these curly braces. This set of polygons, this set of polygons is the same as this set of polygons. They look the same, right? I think you can agree with that. That this is base 43, this is base 54. So 43, 54, base 211, denominator 211. Those numbers, I don't see a very obvious relationship between them. What I did was I gathered those numbers just to see what I can find out about them. Whoops. But I can't make any sense of these. So the ones that gather into one polygon, these are the pairs that form the same polygon. 17, 149, base 22, base 48. Those pairs of polygons are the same. These are the ones that form 2 polygons, that form 3, that form 5, 6, 7, 10, 14 polygons, 15, 21, 30 polygons, 35, 42, and 70. I'll just show you the ones that form 70 polygons with my handy browse function. Yeah, these are of course just triangles because they are because there are 70 different ones in base 211. 210 divided by 70 is 3, therefore you're getting these triangles. But this set of triangles, there are 70 of them. This set of triangles is the same, identical to this set of triangles. But one set, I'm sure, is being drawn clockwise, and the other one is being drawn counterclockwise. But just look at that first line of them. That first line of these is the same as the first line of these. I think you can be convinced just visually of that. Okay, so of the 210 available bases, I actually have 105 pairs of polygon sets that are just identical with each other. Okay, and so the last sort of modular arithmetic question for our team is there a formula to determine which bases create twin polygons or polygon sets? For example, in n over 211 base 2, that image is exactly the same as n over 211 base 106. There is an intriguing way to start this, which is to realize that that 106 is half of 210, half of 210 plus 1. And then if you look at base 3, its colleague is where is it? Yeah, base 3 is 141. Well, 210 divided by 3, 70, 70, 140. 141 is one off from 2/3 of the base. But that pattern, say, 106 is 1 off from half the base, half the of the denominator, and 141 is off by 1 from 2/3 of the denominator. But I would like to know if there is some formula given 2 and 211 that spits out 106, but also given 57 it spits out 174, or if you input 174 it spits out 57. Okay, so I don't know what these numbers have to do with each other. That's again a modular arithmetic question that I don't know how to solve. And so for your entertainment, I'm going to put all of the sort of modular arithmetic questions that we have into the description of this video, and let you puzzle them out for yourself. Okay, so thank you all for listening, and get in contact with me if you have any ideas. Thanks for your time.